Let's look at Lagrange multipliers. This is a great technique for constrained optimization. And in any kind of constrained optimization problem, whether you use Lagrange multipliers or not, you have the same kind of setup. And that is that you've got some sort of function you want to maximize or minimize. That's called the objective function. In this case, it's going to be 8x plus 6y for our first example. And we don't just want to find the max or min on the whole plane for any x and y. That's often stupid. Here it's just be infinity and minus infinity. It just goes off to in both directions. Instead, we have some sort of set. The constraint set, in this case, it's going to be a circle, the circle of radius 5, the center of the origin, x squared plus y squared equals 25. And we're only interested in points on that constraint. So often it's something like the constraint is what materials you have available to build your object, perhaps, and the objective function is the volume or the surface area or the profit you make by building this object or something like that. Okay, and we're going to focus on the case, which is very typical, where the constraint set is the level set of a function. We're going to call that function g. So this function g is the constraint function, and it is set equal to a known fixed constant. Excuse me. Whereas the objective function is something we want to, it's not set equal to a constant. We want to make that as big or small as possible. Okay, so one way to approach constraint optimization is to parameterize your constraint set, and you could do something like x equals like 5. That's a 5, not an s. Ooh, it didn't make it much better. There we go. 5 cosine t, y equals 5 sine t, something like that, and turn it into a one variable problem. In this case, that wouldn't be too bad, but it's a lot more sophisticated than we need in this case. And there's a lot of times when it's either impossible or very hard and very messy to parameterize a level set like this. Okay, so we're going to use a technique that avoids that process and really uses this in its native form. Okay, so here's the observation, and that is that if our constraint set is the level set of G, let's use our ability to describe F in terms of level sets and see what happens, because that'll sort of bring them into a parallel footing. So I'm going to draw the level sets of F. Those are just going to be 8x plus 6y equals some constant. Not hard to see that those are straight lines like this. And as x and y get bigger for this particular function, that's the direct direction of increasing f. Okay, so, and in particular, 8x plus 6y equals a constant, that happens to be a bunch of lines that are perpendicular or orthogonal, just like when we do like planes in space, things like that. They all have the same common normal vector. N is 8, 6. It turns out that's going to show up in a different way very soon. Okay, so from that description, that geographical description is pretty obvious what the answers are, at least sort of pictorially. If I want to have to stay on this circle and I want to climb up the level sets of f, I better be on that level set. That's the last one that touches. And if I want to get, so that's going to be the max. If I want to get to the min, then I better be over here. That's the lowest level set that touches. And we just need to make a few geometric observations that are the key to how Lagrange multipliers works. So the first observation is that at an extremum, at a max or min, the level set of G is parallel to a level set of F. And you can see that it's coming into, they're really tangent. Okay, so they're in a parallel direction. And that's because if I'm going to be at a max and I'm going to be constrained to this set, to the circle here, then I'm not allowed to cut through the level sets of F. For example, here, this is not a max because I can very easily stay on the constraint set and yet climb up the ladder of F to get a bigger value or climb down. The only way that's not going to happen is that when just a little bit of wiggling on the constraint set G doesn't give me any change in the function. So it's really about wiggling the point I'm at, but only wiggling it on the constraint set. I'm not allowed to go off the constraint set. That's not legal. And seeing what happens. This is the kind of point where that doesn't change to first order. It doesn't change the value of f. And here's another one where it doesn't change the value of f. Anything else, it's really easy to make f bigger or smaller, even if I'm forced to stay on the constraint set. Okay, so that is really the key geometric observation. Okay, well, but what's another way to talk about level sets of a function? The gradient is a really good tool. Okay, so the next observation is that the gradient of f is orthogonal to the level set of f, and same thing for g. One thing to notice here, I want to mention, f and g had nothing to do with each other. This was a constraint. This was another function coming in that I was trying to maximize or minimize. They don't have a particular relation coming in here, but by describing them both in terms of level sets, we've got a couple of very parallel statements about how f and g are behaving at one of these special points. Okay, this is only true when we found an extremum. That's what links the two functions together. Don't assume that somehow these two functions must have come with this kind of information. It's that at the extremum this link happens. Okay, so all right, so if the level sets are parallel and the gradients are perpendicular to those level sets, well, so here's a gradient of g. Hopefully you can see that. It's getting a little busy. And then maybe here is the gradient of f. They have to be in exactly the same direction. They're parallel to each other. Okay, and that's a very algebraic statement. So they're parallel to each other, or in other words, the gradient of f is some multiple of the gradient of g. And traditionally we use lambda. It's a Greek L. It may or may not stand for Lagrange. I'd have to look up the history to make sure if it really stands for Lagrange, or if Lagrange just thought lambda was a cool letter. Okay, so we have that the gradient of f is some mystery constant times the gradient of g. So one weird thing about this is it brings in this mystery constant, and in a lot of problems we don't actually care too much about what lambda does for us. You can get a little more sophisticated and talk about the meaning of lambda, which I won't write right away. But this is just a nice way to say when two vectors are parallel to each other. If they're in the same direction, one is a scalar multiple of the other. And we always typically say it as gradient of f is lambda times gradient of g. Okay, so what does that mean in this case? Let's get that's really the whole general theory for this, at least this particular special use of Lagrange multipliers. It can get more complicated later, but that's about it. So gradient of f in this case is, oh yeah, it's 8, 6. There's that normal vector coming in again. Ah, that isn't a coincidence. That the common normal vectors to all these level sets, all these lines, is going to be significant in this problem. Now in general, this is going to have variables because f is not going to be just a linear function. But here it's just linear because I picked a simple example. Gradient of g, okay, that's this guy. That's 2x comma 2y. Okay, so we could say it in vector form as 8, 6 has to be some mystery constant, the Lagrange multiplier. So that is, in fact, the Lagrange multiplier. Lambda is that quantity. It's the name for it. Lambda times 2x, 2y. And we almost always just break that out right away into two scalar equations. Okay, so these are two very, very important algebraic equations. Here they're not particularly intimidating. Nothing weird, no cosines, no sines, no square roots, nothing like that. But it's a little weird that we've added a variable, this Lagrange multiplier. We're not sure its meaning. We don't think we absolutely need it to solve the problem of just what is the x and y coordinates of this point, or what's the x and y coordinates of this point. And we seem to only have 2 equations and 3 unknowns, which would be very bad, okay, which would be indeterminate. But remember, the one thing we haven't used yet is which circle we're on. All I've used so far is the nature of the function g, that is x squared plus y squared. And now we have to remember, oh yeah, there's another equation here. The constraint equation is another piece of information, okay? So these 2 equations actually would describe all of the maxima and minima on any circle of any radius compared to this function f. And so that would be like this point in this circle, this point in this circle, this point in the circle, this point in the circle. And once you actually specialize to one of the constraint sets, which you almost always have, then you get your third equation. Okay, so it's getting a little long, but let's just go ahead and solve this. Okay. You know what? I'm just going to erase almost everything here. Okay. Okay, so what do we need to do here? Well, there's various ways. This is where the algebra can get a little tricky, and it really depends case by case, and you have to do a number of examples to get it right. But I want to solve this system of equations. And one way you can do that is sort of isolate the lambda and use that as a tool to figure out what's going on with x and y, or you could use lambda to relate these two equations to each other. I would say probably your best bet here is just to try to get these equations to talk to each other right now. And that would say that x is going to be 8 over 2 lambda. Okay. And y is 6 over 2 lambda. Well, of course, this is just 4 over lambda. And this is just 3 over lambda. Okay, so that's giving a very close to a direct relationship between x and y. So in fact, clearly x is just 4/3 times y. Okay, so in this case, there's lots of ways to get to this conclusion, but we've now eliminated lambda, basically. So let me just write it out. So, x is 4/3 y. Okay, now we can put that in the constraint equation. Often the constraint equation gets used last. Not always. And again, lots of examples are usually necessary at this point to get used to the algebra. Okay, so now I'm just going to plug that in. 4/3 y squared plus y squared equals 25. 16/9 plus 9/9 times y squared, just factoring out the y squared, equals 25. And yes, I did pick a nice set of numbers. We're getting 25 y squared equals 25 times 9, clearing the fraction. Y equals plus or minus 3. And then, of course, we have this equation for x. X equals plus or minus 4. So you might have seen that coming. Let me redraw the picture anyway. Not too surprising that the points that are orthogonal to these things with a slope of minus 3/4 are these guys where the coordinates are 4, 3 and minus 4, 3. I guess the slope is minus 4/3 actually. Okay, and this guy has a slope of 3/4. So not too surprisingly, it's all about tangents to circles being orthogonal to radial directions in circles, because I picked a special example where we have a very nice special constraint set, a circle, and very nice special level sets for our objective function, straight lines. Okay, ooh, minus 4, minus 3. Forgot the minus sign there. Okay. So the main theory is, how do you set up these equations, the lambda equations, and combine them with a constraint? And then the details are about exactly how you do all the algebra that's involved. And I'll do a little more intricate example in the next video.